Hello, students. Today we're going to look at the hybridization of atomic orbitals. This is just in continuation of molecular geometry. Once you know the number of electron clouds, then it is easy for you to know what is the hybridization. Okay, let's start with the introduction to that.
A covalent bond forms when orbitals of two atoms overlap. This overlap is occupied by a pair of electrons having high probability of being located between the nuclei of two atoms. Linus Pauling proposed that the valence atomic orbitals in a molecule are different from those in the isolated atoms. These valence atomic orbitals lead to more stable bonds and are consistent with the observed molecular shapes. The process of orbital mixing is called hybridization. The new atomic orbitals are called hybrid orbitals. There are 5 common types of hybridization. The spatial orientation of each type corresponds with the arrangement of electrons as predicted by the VSEPR model. SP hybridization. When there are 2 charge clouds around the central atom in a molecule, the geometry of the molecule is linear. For example, in beryllium dichloride, the orbital diagram for the valence electrons in the beryllium atom is: in its ground state, the electrons are paired. Hence, the beryllium atom will not form a bond with the chlorine atoms. However, as the chlorine atoms come closer to the beryllium atom, one of the 2s electrons is promoted to the 2p orbital. Now there are 2 orbitals in the beryllium atom available for bonding. One chlorine atom would share the 2s orbital. The other chlorine atom would share the 2p orbital. This will result in 2 non-equivalent beryllium-chlorine bonds. However, experiments suggest that the 2 beryllium-chlorine bonds are equivalent in every respect. Thus, the 2s and the 2p orbitals in the beryllium atom must be hybridized to form 2 equivalent sp hybrid orbitals. The 2 hybrid orbitals lie on the same axis so that the angle between them is 180 degrees. Thus, each beryllium-chlorine bond is formed by the overlap of a beryllium sp hybrid orbital and a chlorine 3p orbital. In general, central atoms of molecules having 2 charge clouds have sp hybridization.
All right, let's look at the general trend here. Now, when you have 2 charge clouds, you will get sp. So just remember that each one of these will represent electron cloud. This 1, 2. When you have 3 charge clouds, you're going to have sp2. That means 1 and then plus 2 making 3. If you have 4 charge cloud, you're going to have sp3. So 3 plus 1, 4. Right, that's just the trend. When you are looking at once you know the charge clouds, then it is easy for you to just predict the hybridization. All right.
When there are 3 charge clouds around the central atom in a molecule, the geometry of the molecule is trigonal planar. For example, in boron trifluoride, the orbital diagram for the valence electrons in the boron atom is: in its ground state, there are 3 valence electrons, 1 pair in the 2s orbital and 1 unpaired in the 2p orbital. As the fluorine atoms come closer to the boron atom, one of the 2s electrons is promoted to the 2p orbital. Now there are 3 orbitals in the boron atom available for bonding. The 2s and 2p orbitals in the boron atom hybridize to form 3 equivalent sp2 hybrid orbitals. The 3 hybrid orbitals lie in the same plane so that the angle between any 2 fluorine atoms is 120 degrees. Thus, each boron-fluorine bond is formed by the overlap of a boron sp2 hybrid orbital and a fluorine 2p orbital. In general, central atoms of molecules having 3 charge clouds have sp2 hybridization.
I hope you can see the pattern now.
When there are 4 charge clouds around the central atom in a molecule, the geometry of the molecule is tetrahedral. For example, in methane, the orbital diagram for the valence electrons in the carbon atom is: in its ground state, there are 4 valence electrons, 1 pair in the 2s orbital and 2 unpaired in the 2p orbital. As the hydrogen atoms come closer to the carbon atom, 1 of the 2s electrons is promoted to the 2p orbital. Now, there are 4 orbitals in the carbon atom available for bonding. The 2s and 2p orbitals in the carbon atom hybridize to form 4 equivalent sp3 hybrid orbitals.
Remember that when we draw the orbital diagram of carbon, carbon has 6 valence electrons, and the configuration is 1s2, 2s2, 2p2. Okay, so if you draw this first orbital diagram is that, the second one is this, and the third suborbital is this. So in other words, you have 2 here. You're supposed to have 2 here, right? And then 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Oh, okay, sorry, this is free because you have 6. Yeah, you have 6. You have 6 electrons to distribute. So you have just change the color. You have 1 here and 1 here. All right. Now this section is empty. So this is 1s2. This is 2s2. And this is 2p2. So what happened is 1 electron from the 2s2 is excited and fill this section. So this one disappears and you have 1 here. And that is what I was trying to explain. It's like in the excited state of electron configuration, so that this one becomes 2s1 and then this becomes 2p3. That's why you have sp3 hybridization overlapping. So this is S and P3.
Charge clouds around the central atom. In a molecule, the geometry of the molecule is trigonal bipyramidal. For example, in phosphorus pentabromide, the orbital diagram for the valence electrons in the phosphorus atom is: in its ground state, there are 5 valence electrons, 1 pair in the 3s orbital and 3 unpaired in the 3p orbital. As the bromine atoms come closer to the phosphorus atom, one of the 3s electrons is promoted to the 3d orbital. Now, there are 5 orbitals in phosphorus atom available for bonding. The 3s, 3p, and 3d orbitals in the phosphorus atom hybridize to form 5 equivalent sp3d hybrid orbitals. The 5 hybrid orbitals are arranged in a trigonal bipyramidal geometry such that the bond angles are 90 degrees, 120 degrees, and 180 degrees. Thus, each phosphorus-bromine bond is formed by the overlap of a phosphorus sp3d hybrid orbital and a bromine 4p orbital. In general, central atoms of molecules having 5 charge clouds have sp3d hybridization. When there are 6 charge clouds around the central atom in a molecule, the geometry of the molecule is octahedral. For example, in sulfur hexafluoride, the orbital diagram for the valence electrons in the sulfur atom is: in its ground state, there are 6 valence electrons, 1 pair in the 3s orbital, 1 pair and 2 unpaired in the 3p orbital. As the fluorine atoms come closer to the sulfur atom, one of the 3s electrons and one of the paired 3p electrons are promoted to the 2 3d orbitals. Now, there are 6 orbitals in the sulfur atom available for bonding. The 3s, 3p, and 3d orbitals in the sulfur atom hybridize to form 6 equivalent sp3d2 hybrid orbitals. The 6 hybrid orbitals are arranged in an octahedral geometry such that the bond angles are 90 degrees and 180 degrees. Thus, each sulfur-fluorine bond is formed by the overlap of a sulfur sp3d2 hybrid orbital and a fluorine 2p orbital. In general, central atoms of molecules having 6 charge clouds have sp3d2 hybridization.
And those are the required hybridization that we need to know. We have only 6 hybridization, sp to sp3d2, making 6, and that is the highest one we need to know.
Molecule AB2. Total number of charge clouds, 2. Geometry, linear. Hybridization, sp. Molecule AB3. Total number of charge clouds, 3. Geometry, trigonal planar. Hybridization, sp2. Molecule AB4. Total number of charge clouds, 4. Geometry, tetrahedral. Hybridization, sp3. Molecule AB5. Total number of charge clouds, 5. Geometry, trigonal bipyramidal. Hybridization, sp3d. Molecule AB6. Total number of charge clouds, 6. Geometry, octahedral. Hybridization, sp3d2. Note: 1. The concept of hybridization is a theoretical model used only to explain covalent bonding. 2. Hybridization is the mixing of at least 2 non-equivalent atomic orbitals. 3. A hybrid orbital has a very different shape than an atomic orbital. 4. The number of hybrid orbitals generated is equal to the number of atomic orbitals that participated in the hybridization. 5. Covalent bond in polyatomic molecules and ions is formed by the overlap of hybrid orbitals. Electronegativity is a property that helps distinguish bond polarity. Consider hydrogen fluoride molecule. The atoms in the molecule are covalently bonded. Fluorine atom is more electronegative than hydrogen atom. Hence, the hydrogen and fluorine atoms do not share the bonding electrons equally. This unequal sharing of the bonding electron pair results in a relatively greater electron density near the fluorine atom and a correspondingly lower electron density near the hydrogen atom. The difference in the electronegativities of covalently bonded atoms results in a polar covalent bond. The difference in the electronegativities of atoms in a covalently bonded molecule results in a molecule having a dipole moment. Dipole moment is a vector having both magnitude and direction. Since the electron density is greater towards fluorine atom, the dipole moment is indicated by an arrow pointing towards fluorine atom. The arrow has a positive mark on hydrogen atom, indicating that the hydrogen atom is more electropositive than the fluorine atom. Molecules having a dipole moment are called polar molecules. Thus, hydrogen fluoride is a polar molecule. In considering the polarity of a molecule, one also has to consider the geometry of the molecule. Consider water. From VSEPR theory, we know the arrangement of electrons around the central atom is tetrahedral. Because there are two bonds and two lone pairs on the central atom, the geometry of water is bent or V-shaped. Since oxygen atom is more electronegative than hydrogen atom, the bond polarity is represented as arrows pointing towards oxygen atom. Thus, water has a dipole moment, and it is a polar molecule. Like dissolves like. Thus, polar molecules dissolve in solvents made of other polar molecules. Consider carbon tetrachloride. From VSEPR theory, we know the arrangement of electrons around the central atom is tetrahedral. There are 4 bonds and no lone pairs around the central atom. Thus, the geometry of carbon tetrachloride is tetrahedral. Chlorine atom is more electronegative than carbon atom. There are 4 chlorine atoms. At first glance, it may appear as though carbon tetrachloride would be polar. The polarity of each carbon-chlorine bond points towards the chlorine atom. Because of the tetrahedral geometry of carbon tetrachloride, the bond polarities cancel out. Hence, carbon tetrachloride has no dipole moment. Molecules that have no dipole moment are called nonpolar molecules. Like dissolves like. Thus, nonpolar molecules dissolve in solvents made of other nonpolar molecules.
Right, this is the bond and molecular polarity. Just added just a bit of this to that. And now let's look at some questions on hybridization now. All right, question number 1, which is 16. Number 1 to 15 has been given to you previously. So these are just questions on hybridization. Identify the hybridization of beryllium in BeCl2. Write your answer down in your Google Classroom and probably share the document with me in the class under the classwork. 2, the hybridization of the central atom in a molecule is described as sp. The arrangement in space of the hybrid orbitals about the central atom is blank. Octahedral, tetrahedral, trigonal, planar, and linear. 3, the hybridization of the central atom in a molecule is described as sp3. The arrangement in space of the hybrid orbitals about the central atom is blank. Tetrahedral, linear, trigonal, bipyramidal, trigonal, planar. 4, the hybridization of the central atom in a molecule is described as sp3d2. The arrangement in space of the hybrid orbitals about the central atom is blank. Trigonal, planar, octahedral, tetrahedral, none of the above. Identify the hybridization of sulfur in sulfur dioxide. remember, it's better to draw the orbital diagram in the molecular geometry, and then you know how many charge clouds are available. And that's corresponding to the SP, SP3, SP2, or SP3D. Identify the hybridization of phosphorus in PCl5. If a molecule has a VSEPR formula AB3E, then the hybridization of the central atom is blank. So think of an example of AB3E. Identify the set of hybrid orbitals used by SiF6 -2, that is, has a charge of -2. So the best thing is to draw the molecular geometry. Remember, this is a -2 charge, so it's going to be plus 2 electrons when you count the number of electrons before you draw the structures. The hybridization of A in AB4E2 is sp3d2. The shape of the molecule is blank. So this is if you have 1, 4, 6, so 5, means 6 electron charge cloud. What will be the shape of the molecule? Identify the hybridization of iodine in IF5. IF5. Identify the polar molecule. That is, which of these will have a polar structure? Identify the non-polar molecule. Water is polar. Identify the molecule that is soluble in water. So that means like dissolves like. So what you're looking for should also be polar. Before a polar can dissolve in another substance, that substance must be also in polar shape. Select the response that contains all characteristics applicable to PCl3. You have trigonal planar sp2 hybridization phosphorus atom, 1 lone pair of electrons on P, or polar molecules. So which of these combinations will fit that? Identify the molecule that has a dipole moment. Dipole moment. Okay, this one is not part of it. We have not gotten to ponder that. So I'm going to pause this question here.